What is time, really? Not those judgmental numbers on your lock screen at 2 a.m., or the awkward silence that follows when someone says, "We need to talk," but the actual thing, time itself. It's one of the most familiar aspects of our lives, and yet, the more we try to define it, the less it seems to make sense, like socks disappearing in the wash, only with slightly larger consequences. Tonight, we'll quietly unravel this question, not just how we measure time, but what it is. We'll look at how humans first noticed time's passage, how science now describes it, and why your feet might technically be younger than your head. Along the way, we'll drift through quantum physics, relativity, and the faintly unsettling thought that time might not flow at all. For something that governs everything we do, from the orbit of planets to the aging of bananas. Time turns out to be remarkably slippery. It feels steady and one-directional. But is it? What if time is just the result of things changing? What if the past, present, and future all exist at once, and we're simply experiencing them in order because our brains are too limited to do otherwise? Time appears to have a direction. It moves forward. We grow older, never younger. Ice melts but doesn't unmelt. But physics, in many ways, doesn't demand this forward motion. The fundamental laws work just as well backwards, which is lovely. Nothing like discovering that your entire sense of reality is a convenient biological illusion. Still, time gives structure to the universe. Without it, there would be no before or after, no cause or effect, no way to tell whether the universe is doing anything at all. In fact, some theories suggest time might be more of a side effect, something that emerges when lots of things interact, not a physical thing, but a result of other things happening, like queues in supermarkets. We'll explore these ideas not with dramatic urgency, but with slow, careful observation. From the ticking of a mechanical clock to the way black holes twist time near their edges, from the history of how humans tried to tame time, to what the future might look like when the stars finally go out. It's a story not of answers, but of understanding. A little clearer, a little stranger. By the end, we might not have caught time in a bottle, but we'll have seen its outline. We'll have walked through deep time, bent time, frozen time, and maybe even questioned whether time exists at all. And we'll do so knowing that, either way, it's passing. Quietly, indifferently. This leads us to consider how we begin to frame such a question. What exactly are we asking when we ask, "What is time?" Time surrounds everything we do. We speak of it constantly. Being on time, wasting time, needing more of it, running out of it. But beneath all that day-to-day urgency sits a question far stranger than it first appears. What exactly is time? Not how we use it or how we measure it, but what it fundamentally is. That's the puzzle. At first glance, the answer seems obvious. Time is the thing that keeps everything from happening all at once. It separates before from after. But try to explain it beyond that, and things get awkward. Is time something physical? Does it flow? Does it even exist independently of events? Or is it just our way of making sense of change? Scientists, philosophers, and the occasionally confused physicist have offered a wide range of answers. To Newton, time was absolute, a sort of cosmic stopwatch ticking evenly for everyone, everywhere. Einstein disagreed. He showed that time is relative, stretchy, and affected by speed and gravity. So much for keeping it simple. Philosophers haven't helped much either. Some argue time isn't a real thing at all, just a mental construct we've invented to track change. Others say that past, present, and future all exist equally, and we're just crawling through them like passengers on a very slow train that never stops for snacks. The problem is that time is so tightly woven into everything else that pulling at its thread begins to unravel other big ideas, like causality, memory, and even free will. If time isn't what we think it is, then our understanding of how the universe works might need rethinking too, which is inconvenient. What we can say is that time plays an essential role in the laws of physics. Every equation that describes how things move or interact includes time as a key variable. And yet, many of those equations don't seem to care whether time goes forward or backward. It's as if the universe itself isn't particularly fussed about direction. Only we are. So tonight, we'll gently explore the full scope of this mystery. We'll look at how time behaves at the everyday level, and how it shifts when viewed through the lens of relativity and quantum theory. We'll consider the deep implications of time's direction and what the latest science says about whether time had a beginning or whether it might eventually end. This leads us to consider how we, as individuals, experience time, not as an abstract puzzle, but as something that shapes our lives every moment. You've probably noticed that time doesn't always behave. Not scientifically, it's consistent there. But personally, it's a different story. 5 minutes waiting for a bus in the rain feels longer than an hour scrolling past videos of dogs wearing jumpers. Time, at least as we experience it, is inconsistent, moody, and occasionally rude. It shapes our lives from start to finish. We celebrate birthdays, regret missed chances, count down to holidays, and set alarms we fully intend to ignore. We measure life in school terms, shifts, weekends, and deadlines. Time runs our routines, yet almost none of us stops to ask how it works. We just assume it's there, steady, predictable, fairly annoying on Mondays. This everyday sense of time, what you feel passing from moment to moment, is shaped by your biology. Your internal clock, known as the circadian rhythm, keeps your body in sync with the 24-hour cycle of Earth's rotation. It helps determine when you sleep, eat, and feel alert, or not alert, depending on how much caffeine you've had. But there's more. Your brain creates your sense of time based on how much is happening. When lots is going on, time feels like it stretches out. When things are repetitive or boring, it speeds up in memory. That's why childhood summers felt endless, and why adulthood feels like someone sat on the fast-forward button. Your perception of time is also affected by emotion. Fear can make a few seconds feel stretched, while joy or flow compresses hours into what feels like minutes. It's less like watching a clock and more like watching your own brain guess at passing moments, and it's not always good at it. Even memory plays tricks. You remember events in order, but your recall isn't a perfect timeline. It's patchy, uneven, gaps filled with assumptions. The brain isn't a recorder, it's a storyteller. And it edits heavily. You're experiencing not just what happened, but your version of what happened, stitched together with a narrative thread, a thread that assumes time flows forward. And we take that flow for granted. Time has a direction, right? We remember the past, not the future. We grow older, not younger. Cause comes before effect. This all feels natural. But is it? Physics doesn't always agree. Some laws don't care which direction time goes in, as long as everything balances. This leads us to consider whether our personal experience of time, so central to our lives, is actually telling us the truth about how time works in the universe. Time seems straightforward enough when you're just living it. The sun rises, breakfast happens then. If you're lucky, lunch. Clocks tick, shadows move, and people age. Everything you can observe suggests that time is real, flowing smoothly from one moment to the next. But this direct experience, convincing as it is, doesn't necessarily show us how time works. It shows us how we interpret it. We're wired to notice change. A tree growing, a kettle boiling, a phone battery draining far faster than it should. These are events. And events give us the impression that time is passing. But what we're actually detecting is motion, not time itself. We see objects changing position or state, and from that, we infer a sequence. That sequence feels continuous because our senses and memory stitch everything together. Your brain is constantly updating a mental timeline based on what it sees, hears, and remembers. If the world suddenly paused, but your thoughts didn't, you wouldn't even notice the break. Time might feel like it's flowing, but the sensation is coming from inside your own head. Clocks, of course, offer a sense of objectivity. Mechanical, digital, atomic. They all tell us what time it is. But these devices don't measure time itself. They measure regular motion. The swinging of a pendulum. The oscillation of quartz. The vibration of atoms. They provide a standardized count of consistent changes, which we then call seconds or hours. In other words, they track change, not time directly. What this means is that our entire sense of time is built on observing change and labeling it. Without change, there'd be no way to tell whether time was passing at all. If every atom in the universe suddenly froze in place, how would you know time hadn't stopped? You wouldn't. You'd just be paused. Though admittedly, that would be one way to avoid doing your homework. This raises an uncomfortable idea. Maybe time isn't some background river everything moves through. Maybe it's just a label we apply to the order in which things happen. The ticking hands on a clock don't show time itself. They show movement that we've agreed to treat as a measure. A bit like deciding traffic lights define motion. They don't. They just regulate it. So our direct experience, so vivid, so reliable, is not a scientific explanation. It's a useful perception built on biological and cultural tools. It works well enough to get you to school on time. But it might not help much if you're trying to understand what time is at the level of atoms or black holes. This leads us to consider how our limited human scale affects what we can perceive, and how time might look very different when we zoom far out or far in. We've seen how your personal sense of time is shaped by memory, perception, and your alarm clock being wrong half the time. But if we want to get closer to what time really is, we need to move beyond human experience. Time doesn't just operate on our daily scale. It stretches from the tiniest quantum events to the lives of stars and galaxies. On the microscopic end, time ticks along in billionths of a second. Atomic clocks, for example, use the vibrations of atoms to measure time with stunning precision, far more accurately than anything your smartphone could manage, especially if it's still trying to update itself every morning at 3 a.m. At these scales, time doesn't feel like a smooth flow. It becomes a series of measurable intervals tied to very small, very regular changes. Zooming out, time also plays out over cosmic distances. Light from some of the stars we see tonight left its source millions, or even billions of years ago. That means When you look into the night sky, you're not just looking across space. You're looking through time. The further away something is, the further back in time you're seeing, which makes stargazing slightly more meaningful and slightly more unsettling. Then there's geological time. The slow movement of continents, the layering of rock, the rise and fall of species over millions of years. The Earth doesn't care about our weeks and months. It runs on processes that make a century look like a hiccup. It's humbling in a way, knowing that most of what has happened on this planet did so without us and will continue to do so long after we're gone. And yet, despite these wildly different timescales, there's something oddly consistent. Whether it's a radioactive particle decaying in microseconds or a black hole slowly evaporating over trillions of years, change still happens. Events still have order. Time, as a dimension, still applies. Just stretched or compressed, depending on the system you're observing. To help make sense of these differences, scientists often use analogies. If the entire history of the universe were a 24-hour day, modern humans would appear only in the last few seconds before midnight. Dinosaurs came and went around 11:39 p.m. And your morning commute? Probably somewhere between 11:59, don't even bother. These comparisons help highlight just how narrow our daily experience of time really is. Most of the universe operates at scales and speeds we can barely imagine. But time still applies. It's still part of the equation, even if we're not the main audience. This leads us to consider how science begins to define time. Not through feeling or analogy, but through mechanisms we can study, measure, and test. If time doesn't flow like a river or tick like a metronome, how do scientists actually define it? The simple answer is, they don't, not completely, but they do measure it, very precisely, by using changes in physical systems. In science, time is often treated not as a thing in itself, but as a way to keep track of how other things behave. Let's start with something familiar. A clock, whether it's digital or ancient, and full of gears, measures time by counting repeated motions. The Earth rotates, a pendulum swings, an atom vibrates. These repeating processes are used to divide time into equal units: seconds, minutes, hours. So, time isn't measured directly. It's inferred by tracking change that happens regularly and predictably. Today, our most accurate timekeeping comes from atomic clocks, which rely on the vibrations of atoms, usually cesium. When energized, a cesium atom vibrates at a consistent frequency, 9,192,631,770 times per second, to be exact. We've decided that this is what a second is: precise, reliable, and entirely indifferent to whether you're running late or not. From a physics perspective, time is treated as a variable, something that lets you describe when an event occurs. In equations, it's a parameter, just like distance or mass. For instance, Newton's laws describe how objects move through time, but they never explain what time is. It's just there, quietly sitting in the background, waiting to be filled with stuff happening. In classical physics, think Newton. Time was assumed to be absolute. That is, the same for everyone, everywhere. A kind of invisible grid ticking along, independent of what's going on. But this idea starts to unravel when you look closely, or move quickly, or stand near a black hole, all of which, let's be honest, are rarely part of a school timetable. The real shift came when scientists began asking whether time always behaves the same, regardless of perspective. Does it tick at the same rate for someone standing still and someone zooming past in a spaceship? It turns out, no, it doesn't. And that raises a problem, because if time doesn't behave consistently for everyone, then maybe it's not the simple, universal backdrop we thought it was. This realization sets the stage for one of the most important ideas in physics. That time is not fixed. It can bend, stretch, and slow down depending on where you are and how fast you're going. A bit like how weekends feel shorter if you're enjoying them. Except this isn't psychological, it's baked into the structure of the universe. This leads us to consider how time really works when observed more carefully. How it interacts with motion, space, and gravity on a deeper level. Once we accept that time doesn't tick the same way for everyone, we have to rethink what it means for time to pass at all. This is where Albert Einstein made things rather complicated. Though in fairness, he also made them much more accurate. He showed that time is not a separate entity ticking away in the background, but part of something bigger, space-time. Space-time is the idea that time and space are linked into a single four-dimensional framework. You don't just move through space, you move through time as well. And your position in one affects how you experience the other. Time, it turns out, doesn't exist in isolation. It bends and shifts along with the fabric of the universe. According to Einstein's theory of special relativity, time slows down the faster you move. This isn't a metaphor, it literally slows, but only from the perspective of someone watching you. If you were the one speeding along in a spacecraft, your wristwatch would tick normally for you, but people on Earth would see your time running more slowly. Handy if you're trying to avoid birthdays. This effect, called time dilation, becomes noticeable at speeds close to the speed of light. But even at everyday speeds, it technically exists. It's just so minuscule that you'd need incredibly sensitive instruments to detect it. The fact that your car clock doesn't noticeably lag behind your kitchen one isn't a failure of physics. It's just that your commute isn't fast enough to matter. Though if you drive like some people on the M25, you might be testing the limits. Then there's general relativity, which adds another twist. Time also moves differently depending on gravity. The stronger the gravitational field, the slower time passes. This has been confirmed by placing atomic clocks at different altitudes. A clock on the floor will tick slightly more slowly than one on a shelf. Your head is aging faster than your feet. Not by much. Fractions of a nanosecond. But still, technically, you're already unevenly old. This bending of time by gravity is crucial for things like GPS. Satellites orbit above Earth's surface where gravity is weaker, so their onboard clocks tick slightly faster than clocks on the ground. Engineers have to correct for this daily. Without adjusting for general relativity, your phone would tell you you're in a different postcode entirely, which, depending on your sense of direction, it might already be doing. What this all suggests is that time isn't a constant backdrop. It's part of the universe's structure, shaped by speed and gravity. And once we see time as part of a flexible fabric rather than a fixed ruler, it opens the door to understanding how it behaves across all scales. This leads us to consider how this behavior plays out from the smallest particles to the vastness of space, where the laws of physics continue to apply with remarkable consistency. So far, we've seen how time can stretch and slow depending on speed and gravity. Now, let's take that idea and apply it across every scale, from the tiniest particles to the largest structures in the universe. Because no matter where you look, time still plays by the same rules. It just wears very different faces depending on the situation. At the smallest level, quantum particles, events happen on unimaginably short timescales. Subatomic particles like muons live for just microseconds before decaying. But even that decay process follows patterns shaped by time. If you accelerate them to near light speed, their lifespan increases. Time for them slows down, just as Einstein said it would. They don't notice. They're far too small to complain. Zoom out, and you'll find the same principles holding steady. The Earth orbits the Sun over 365 days. Galaxies rotate over hundreds of millions of years. Clocks built from atoms, clocks built from planetary motion. They're all ways of tracking time and all rely on consistent laws of physics. The structure is the same, whether you're looking at electrons or elliptical galaxies. This consistency is part of what makes science possible. If the laws of physics didn't apply everywhere in the same way, predicting anything would be a waste of time, literally. But thanks to the reliability of these laws, we can understand and measure time anywhere in the universe. A clock on Mars works just like a clock on Earth, adjusted for gravity and motion, of course, but still ticking. One of the most fascinating examples of this universality comes from GPS satellites. They rely on ultra-precise atomic clocks, and their systems must account for both special relativity, because they're moving quickly, and general relativity, because they're farther from Earth's gravity. Without these adjustments, your sat-nav would put you somewhere near a hedge in Belgium when you're actually just looking for the takeaway down the road. This tells us something profound. The flow of time isn't personal. It's built into the fabric of the universe. But it also doesn't revolve around us. If Earth vanished tomorrow, atoms would still vibrate, stars would still shine, and time, such as it is, would continue, quietly indifferent. And that's the strange beauty of it, from the very small to the very large. From deep inside atoms to the edge of black holes, time follows the same principles. It doesn't change the rules just because someone's watching. It doesn't need to be noticed to work. This leads us to consider time not just in space, but across time itself. How we might begin to understand scales so vast, our lifetimes barely register against them. Up until now, we've treated time as something that varies, slows down with speed, stretches under gravity, ticks differently depending on your altitude. But beneath all of that, time is also something more foundational, a dimension. Like length, width, and height, time allows us to describe where and when something happens. It's not a background setting, it's a coordinate. In physics, especially since Einstein, time is considered the fourth dimension. The first three describe where something is in space. Time tells us when it happens. Together, they form what we call space-time. It's not space and time as separate things, it's one interconnected framework. You don't just exist in space, you exist in time too, whether you like it or not. Here's where it gets a bit uncomfortable. We can move backwards and forwards through space, but time only moves in one direction. You can walk left, right, up, down, or diagonally, but you can't stroll casually into yesterday. This one-way travel through time is something we all take for granted, but science isn't entirely sure why it happens. Physicists call this the arrow of time. It's the idea that time has a built-in direction, from past to future. Broken glasses don't unbreak, you don't suddenly become younger. Eggs, once scrambled, stubbornly refuse to rearrange themselves. This isn't just bad luck, it's how time seems to work, at least from our point of view. Interestingly, the laws of physics don't necessarily require this direction. Most equations in physics work just as well forwards as backwards. That is, they don't prefer one direction of time over the other. This means the arrow of time isn't built into the equations. It seems to come from somewhere else entirely, possibly from how things started out. One popular explanation involves entropy, a measure of disorder in a system. The second law of thermodynamics states that in a closed system, entropy tends to increase. In other words, things become more disordered over time. This gives time a kind of direction, from low entropy more order to high entropy less order. From a neat stack of books to a mess on the floor, essentially. This entropy gradient might explain why time only flows forward. The early universe started in an extremely low entropy state, and it's been increasing ever since. As the universe gets messier, time keeps ticking along with it. Why the universe began in such an oddly ordered state remains one of the biggest questions in science, possibly just to keep physicists busy. What this shows us is that time isn't just a measurement, it's a structural part of the universe. But it behaves in ways that challenge our intuitions, and its direction, though familiar, might be more of a statistical trend than a fundamental law. This leads us to consider the larger reality, that time moves forward, not for our benefit, but simply because the universe doesn't know any other way to behave. By now, we've established that time stretches, slows, bends, and ticks differently depending on where you are and what you're doing. But behind all that complexity is a deeper truth, one that might be quietly unsettling, but also strangely comforting. Time, for all its presence in our lives, simply doesn't care about us. The processes that define time's behavior, atomic decay, the curvature of space-time, the increase of entropy, operate with complete indifference. Your thoughts, memories, deadlines, and birthday parties have no bearing on how the universe keeps time. Whether you're watching the clock or completely ignoring it, time continues. Not slower, not faster, just on. This isn't a failure of meaning, it's a feature of reality. The laws of physics are impersonal. Gravity pulls, light travels, time advances. None of it is directed at you. You don't have to do anything. You don't even have to be here. If every human being vanished tomorrow, planets would still orbit stars, atoms would still vibrate, and the arrow of time would keep pointing forwards. Exactly as it did before we showed up. Take radioactive decay, for example. A single unstable atom doesn't know it's being observed. It doesn't wait for your approval to decay. It does so according to probabilities defined by nature. That process, unfolding at the tiniest scale, is one of the world's most reliable timekeepers. And it doesn't care that your meeting ran long. On a much larger scale, black holes bend time so drastically that near the event horizon, it almost grinds to a halt. Not for any dramatic reason. Not to teach anyone a lesson. Just because mass warps space-time. It's all rather matter of fact. The universe behaves according to physical laws, not personal stories. That includes us, by the way. Our brains construct meaning, memory, and narrative using the flow of time. But those things are byproducts of biology. Our sense of a now is not something the universe needs. It's something our nervous systems produce, so we don't walk into lampposts. The universe, on the other hand, has no particular moment it calls present. There is something peaceful in that indifference. If time passed according to how we felt about it, the whole thing would collapse under the pressure of Mondays alone. Instead, It moves forward with quiet reliability. We may not like that our moments are brief, but we can at least trust that time won't stop just because we're uncomfortable with it. This leads us to consider where this trust in time came from. How human beings began to study its behavior, record its patterns, and search for meaning in the ticking of the world. Long before anyone had heard of relativity or space-time, humans were already trying to make sense of time, though they wouldn't have called it that. They simply noticed patterns. The sun rose and set. The seasons changed. People grew older. Crops followed rhythms. Time wasn't an abstract concept. It was part of survival. And the only clock they had was the sky. Ancient peoples around the world used the movement of celestial objects to track regular cycles. The moon's phases, the rising of certain stars, and the position of the sun on the horizon all became tools for marking time. From Stonehenge to the pyramids, ancient structures show that early civilizations cared deeply about keeping track of the heavens, presumably to avoid missing harvest and, more pressingly, dinner. They developed calendars, some lunar, some solar, and some a combination of both. The Babylonians counted using base 60, which is why we still have 60 seconds in a minute. The Mayans tracked long cycles that spanned thousands of years. The ancient Chinese recorded eclipses. In India, scholars observed planetary motion with remarkable accuracy. Time wasn't just something they felt, it was something they studied. But early observations weren't scientific in the modern sense. They weren't trying to find the nature of time itself. They were building practical knowledge. When should you plant? When will the floods come? Is that star supposed to be there, or is the world ending again? In short, pattern recognition, not physics. Still, this kind of observation laid the foundation for everything that followed. You don't get to Einstein without centuries of people staring at the sky and thinking, that doesn't look quite right. Over time, these cultures began to record their observations, compare notes, and refine their understanding. It wasn't fast, but time, as we've established, isn't in much of a hurry. Perhaps more than anything, early timekeeping revealed a desire for order in a chaotic world. If you can predict the solstice or the return of a comet, you feel slightly less at the mercy of everything else. It's a small comfort to know that, however unpredictable life is, the stars are still on schedule. Unlike, say, public transport or teenagers' sleep cycles. And even in its earliest form, the study of time hinted at something much larger. That change follows patterns, and those patterns can be understood. That events are not random, but part of an underlying structure. A structure that people could observe, measure, and maybe even explain. This leads us to consider how those early insights slowly transformed into something more rigorous. The first steps towards a scientific understanding of time. Once early observers had catalogued the regular rhythms of nature, days, seasons, lunar cycles, some began asking deeper questions, not just when something would happen, but why. This marked the beginning of something more rigorous, trying to understand time as part of a system, not just a schedule. And slowly, methodically, the first scientific ideas about time began to take shape. In ancient Greece, philosophers like Aristotle argued that time was not a thing in itself, but a measure of change. To him, time existed because things moved. If nothing changed, time wouldn't exist. In a way, he was laying the groundwork for future physics, though admittedly without a stopwatch or any intention of doing lab work. Over in India, Thinkers developed detailed systems to track cosmic cycles spanning millions of years. These weren't just for storytelling. They were attempts to explain natural order using enormous timeframes. And in the Islamic world, scholars refined astronomical observations, developed mathematical models, and built mechanical clocks to better measure time. Across cultures, the idea was the same. Time wasn't just something you felt, it was something you could study. During the Renaissance and into the scientific revolution, the conversation shifted further. Time became not just a way to describe change, but something that could be measured with increasing precision. Galileo, for example, studied the swinging of pendulums and falling objects, and began linking time to acceleration. He didn't have a wristwatch, but he had a good eye and a lot of patience. Then came Isaac Newton, who formalized many of these ideas into a full system. In Newton's universe, time was absolute, steady, uniform, and universal. It ticked along independently of anything else, like a cosmic metronome. Time, to Newton, was the stage on which everything happened. It didn't change. It didn't bend. It just moved forward, relentlessly. Like a relative who won't stop talking at dinner. This concept was powerful. It allowed scientists to create models, make predictions, and describe the motion of planets and projectiles with astonishing accuracy. It worked incredibly well. So well, in fact, that no one seriously questioned it for centuries. Which, as we'll see later, was slightly awkward once Einstein arrived. Still, Newton's idea was a massive leap forward. It transformed time from something woven into myth and ritual into a measurable, mathematical dimension. Something you could plug into an equation. Something universal, predictable, and, at least on the surface, completely straightforward. This leads us to consider how these ideas evolved, with new tools and technologies, as humanity began building machines that could track time far more precisely than the human eye ever could. With Newton's framework in place, time became something you could not only think about, but build with. And build we did. If time was a steady, measurable dimension, then the next logical step was to measure it better. The search for precision began, not just for curiosity, but for navigation, science, industry, and knowing exactly how long your tea's been brewing. The earliest timekeeping tools were simple: sundials, hourglasses, and water clocks. These did the job, just not particularly well. Clouds, evaporation, and the occasional spilled sand made things a bit unpredictable. But as trade, astronomy, and scientific research advanced, so did the need for more accurate instruments. Enter the mechanical clock. In the 14th century, mechanical clocks began appearing in European cathedrals and towers. Powered by falling weights and regulated by escapements, they could count hours with reasonable consistency. A huge improvement, though not quite up to the task of timing particle collisions. Still, they introduced the idea of a device that didn't rely on the sun or sand to measure time. The pendulum clock, introduced by Christian Huygens in the 17th century, made things even more precise. Pendulums swing at a steady rate, and that consistency allowed clockmakers to create timepieces accurate to seconds per day. That may not sound impressive now, but at the time it was a leap forward. Especially if you were a sailor trying not to crash into the wrong continent. Fast forward to the 20th century, and timekeeping entered a new era with the invention of quartz clocks. These rely on the vibrations of a quartz crystal when an electric current is applied. Quartz vibrates with remarkable stability, tens of thousands of times per second. The result? Clocks that are accurate to within a few seconds per year, and no need to wind anything. Ideal for people who forget their passwords, let alone mechanical maintenance. But even quartz wasn't enough for modern science. Enter the atomic clock. The most accurate clocks we have use the vibrations of atoms, most commonly cesium-133. 1 second is now officially defined as 9,192,631,770 oscillations of a cesium atom. These clocks are so precise that, if left running, they'd lose less than a second in millions of years, which is a very long time to be early for anything. These tools didn't just improve timekeeping, they reshaped how we think about time. The ability to measure time at such small scales opened new areas of science. Experiments became more exact. Satellite systems could function. Physical theories could be tested in detail. Time became not just something we lived through, but something we could work with, reliably. This leads us to consider how our understanding continued to evolve, not always smoothly, as we discovered that our assumptions about time weren't always correct. As our tools improved and measurements became more precise, something awkward began to happen. Old ideas about time started to crack. Many of the assumptions that had served science well for centuries, like time being absolute and universal, turned out to be not entirely correct, which is just what you want after building your entire worldview around them. Take Newton's concept of absolute time. It worked brilliantly for everyday mechanics. Projectiles, planets, pendulums. But as physicists looked more closely at light, gravity, and motion at high speeds, they found contradictions. Time didn't appear to behave the same for all observers. And when measurements disagree with theory, theory doesn't get the last word. Reality does. One of the biggest shakeups came from Einstein's theory of special relativity. It showed that time depends on your speed. Two people moving at different velocities could disagree about how much time had passed, and both would be right. It wasn't just counterintuitive, it was deeply uncomfortable, especially for those who liked things neat, tidy, and preferably written in Latin. General relativity added another twist. Gravity also affects time. Stronger gravity slows it down. This was confirmed decades later with extremely accurate atomic clocks. Place one on a plane or a tall building, and it ticks slightly faster than one on the ground. So much for time being equal for all. Even your feet and your head don't agree. That's not philosophy. It's physics. Other misconceptions also began to unravel. For a long time, it was assumed that time only moves forward because that's how the universe works. But it turns out the basic laws of physics don't prefer forward over backward. Many equations are time symmetric. They work either way. The one-way feeling we get, the arrow of time, is probably linked to entropy, not to time itself. And then there's simultaneity. The idea that two events can happen at the same time. Sounds simple, but in relativity, simultaneity depends on your frame of reference. Two people in motion relative to each other may disagree on whether two things happened at once. So the phrase, "at the same time," turns out to be rather more complicated than anyone hoped, especially if you're trying to explain it in a group chat. All of these corrections weren't failures, they were refinements. Science moves forward by finding out what doesn't work and adjusting the model. And while it might bruise a few egos along the way, This process has made our understanding of time far more accurate and far stranger than ever imagined. This leads us to consider how these discoveries were tested through carefully designed experiments that revealed what time is really doing, even when no one is watching. If time isn't absolute, doesn't tick the same for everyone, and sometimes seems to disagree with itself, how do we know any of this is true? The answer is simple: experiments. Lots of them. Not dramatic one-off discoveries, but slow, methodical tests carried out by people who patiently poked at nature until it gave them a straight answer. Eventually, one of the most famous tests of time dilation came in 1971, when physicists Haffley and Keating put atomic clocks on commercial aeroplanes. They flew them around the world, then compared them with identical clocks that had stayed on the ground. The result? A measurable difference. Exactly what Einstein predicted. Time had passed more slowly for the moving clocks. A very expensive way to get jet lag. But relativity doesn't only show up in high-altitude experiments. We see it every day in GPS. The satellites that guide your phone's location orbit the Earth quickly and at altitude. That means they're affected by both special and general relativity. Time ticks differently for them because they're moving fast and they're farther from Earth's gravity. Without correcting for these effects, GPS wouldn't work. You'd be 10 kilometers off, which is fine if you're lost in a field, less ideal if you're landing a plane. Experiments also happen at tiny scales. Particle accelerators, like the Large Hadron Collider, send particles racing around at nearly the speed of light. Those particles decay more slowly than they would at rest. Again, thanks to time dilation. Their internal clocks, if they had them, would be ticking more slowly. Fortunately, they don't have time to complain. Even small experiments show the effect. In labs, physicists use atomic clocks placed just a few meters apart, one higher than the other, to measure the change in time caused by Earth's gravity. The difference is tiny, but measurable. A clock just one floor up from another will tick ever so slightly faster, which means technically your upstairs neighbors are aging quicker. Not that they'll admit it. These experiments follow a pattern: build a hypothesis, isolate variables, test, repeat. Scientists go to great lengths to eliminate bias, control for outside effects, and ensure that what they're measuring is real. They compare data over time, share results, and challenge each other constantly. The goal isn't to be right. It's to get it right. Through this careful process, time has revealed itself to be far stranger than we thought, but also consistent. These results aren't isolated flukes. They match theory, they're reproducible, and they've been confirmed in many different ways, across decades, which is how science quite stubbornly makes progress. This leads us to consider how none of this work happens alone. How understanding time has always been a collective effort, built across generations and continents. Understanding time hasn't been the work of one genius with a telescope or a single physicist scribbling equations in a dark room. It's been a collective, slow-building effort across continents, cultures, and centuries. Every major breakthrough has rested on a mountain of earlier work, much of it tedious, often thankless, and occasionally misattributed. Welcome to the group project of the universe. Take Einstein, for example. His theories reshaped physics, but they didn't come out of nowhere. He relied on centuries of groundwork laid by others. Galileo's studies of motion, Newton's laws, Maxwell's equations describing light. Even the mathematics used in general relativity was developed by earlier geometers and theorists. Einstein didn't invent the language, he applied it in an entirely new way. Modern physics is full of this kind of layering. Quantum theories about how particles interact with time draw on the work of dozens of people: Planck, Schrödinger, Heisenberg, Dirac, and many others. No single person figured out how time behaves on its own. It was a network of minds, often working independently, and occasionally arguing in strongly worded letters. And this collaborative effort isn't limited to individuals. Nations and institutions have shared research, equipment, and data, even during times of tension. Atomic clock development, for example, has involved laboratories across the United States, the UK, Germany, and Japan. GPS, though developed by the US military, relies on physics verified globally. Time, it turns out, doesn't respect borders or politics. Across history, knowledge has been preserved, translated, and passed along, sometimes through peaceful cooperation, sometimes through conquest, and occasionally because someone really didn't want to reinvent everything from scratch. Greek astronomy was preserved by Islamic scholars, then translated into Latin centuries later. Indian mathematicians influenced Arabic astronomy, which in turn helped shape European science. It's less a straight line than a web, with surprisingly good memory. Even today, experiments on time require teams of engineers, theorists, programmers, and technicians. The people who design satellites, align lasers, calibrate atomic clocks, and analyze billions of data points rarely appear on the front cover of anything. But without them, none of it works. Science is, quite literally, a shared clock. And in that shared work, something remarkable emerges: consensus. It doesn't mean everyone agrees immediately. Far from it. But over time, evidence accumulates, ideas evolve, and the scientific community adjusts. It's a slow, careful negotiation with reality, one where the final authority is never status or opinion, but observation. This leads us to consider how far that collaborative process has taken us. What time looks like when measured with today's most advanced tools, and what we still don't fully understand. After centuries of staring at sundials and fiddling with pendulums, we've now reached a point where humans can measure time with extraordinary precision. Atomic clocks, those slightly overachieving timepieces, are accurate to within a billionth of a second. That's a level of punctuality few people can relate to, especially if they've ever waited for a delivery that should arrive between 9 a.m. and never. At the heart of modern timekeeping is the cesium-133 atom. When it's energized, it vibrates at a precise frequency: 9,192,631,770 cycles per second. That number isn't just trivia. It defines what a second is. The International System of Units SI now defines time by this atomic behavior. It's not based on the sun or a clock tower, or whether your cat thinks it's dinner time. It's based on the unchanging rhythm of nature at its smallest scale. The accuracy of these atomic clocks isn't just a scientific vanity project. They're essential to many technologies we now rely on daily. GPS, for instance, wouldn't function without relativistic corrections involving time dilation and atomic precision. Satellites need to know not only where they are, but exactly when they are, down to a few nanoseconds. Otherwise, you'd be navigating by guesswork and blind optimism. These clocks also let scientists test fundamental physics. They've been used to confirm time dilation effects predicted by Einstein, and even to detect tiny shifts caused by changes in altitude, differences of just a few centimeters, which means time literally passes faster for your head than your feet. It's not enough to make you dizzy, but it's technically true. You are, in a very real sense, unevenly aged. And the progress hasn't stopped. Next generation atomic clocks, using elements like ytterbium or strontium, aim to be even more precise, accurate to within a second over the entire age of the universe. These aren't the kinds of clocks you'd mount on your kitchen wall. Unless your kitchen also happens to house a laser-cooled ion trap and a PhD in quantum metrology. What's fascinating is that with this growing precision comes growing awareness of our ignorance. We now have tools that are more sensitive than many of the theories we use to explain them. Small variations in how time ticks across different experiments could one day reveal new physics. Subtle hints that our current understanding is incomplete. Yet despite all this technological success, time remains deeply strange. The more precisely we measure it, the more it seems to bend, stretch, and quietly defy our expectations. It behaves differently depending on motion, gravity, and quantum behavior, which is both frustrating and, if you're a physicist, the reason you get up in the morning. This leads us to consider what we still don't know. How time continues to challenge science, and why even the best theories come with questions they haven't yet answered. Despite all our precision tools and elegant theories, time remains stubbornly mysterious. We can measure it exquisitely, manipulate it in equations, and watch it stretch near black holes. But what it actually is, at its core, remains an open question. It's a bit like owning a perfectly functioning smartphone, but having absolutely no idea how the thing actually works. Except it's not a phone, it's reality. One unresolved problem is the origin of time's direction, the so-called arrow of time. The laws of physics work just as well forwards as backwards. A broken glass reforming itself is perfectly fine in the maths, yet we never see it happen. Why does time only move in one direction? The best current answer involves entropy, the tendency for disorder to increase. But that's more of a description than an explanation. Another puzzle lies in the realm of quantum mechanics. At the quantum scale, particles don't seem to experience time in the way we do. Some quantum equations don't even include time as a variable. In other words, our most accurate theory of matter doesn't need time to function, which is awkward considering we appear to be surrounded by the stuff. And then there's the challenge of unifying quantum theory with general relativity. One treats time as smooth and continuous. The other behaves as though it might be granular or even emergent, coming out of more fundamental phenomena we don't yet understand. Trying to make both views agree has been one of the most persistent problems in physics. So far, time hasn't been especially cooperative. Some theories, like loop quantum gravity or causal set theory, propose that time isn't a basic ingredient of the universe at all. It's something that emerges from a deeper, more abstract level of physics. Others, like the block universe model, suggest all points in time exist equally, and the flow of time is just an illusion tied to human perception. Basically, time might be real, or fake, or real but only from certain angles. Not helpful. We also don't know why the universe started in such a low entropy state, which gives rise to the forward flow of time. The Big Bang wasn't just hot and dense, it was oddly ordered. This one strange condition may underpin everything about how we experience time, but no one really knows why the universe began that way. It's a bit like turning up to a dinner party and realizing the table was set before the house was even built. All of this leaves us with a curious situation. The more we understand about time, the more it resembles something we don't understand at all. We're good at measuring its effects, but unsure whether we're observing a thing, a relationship, or just a persistent glitch in our perception. This leads us to consider how human beings experience time, and how our biology, memory, and language shape the way we move through it. Time may be a universal constant in physics, but it's strangely personal in the mind. A minute spent waiting for a kettle to boil feels longer than a minute spent eating cake. Same 60 seconds, wildly different experience. Human brains don't measure time like stopwatches. Instead, we estimate it poorly. And our sense of time is warped by attention, emotion, and memory. When we're bored or anxious, time slows to a crawl. The brain pays more attention to passing moments, which makes them feel stretched out. By contrast, when we're busy or engrossed, time seems to race by. This is partly because we store fewer memories of those periods, so when we look back, there's less to recall, and it feels shorter. Age also affects our perception of time. Children often feel time moves slowly, whereas adults frequently say it flies by. One explanation is proportional. A year for a 5-year-old is 20% of their life. For a 50-year-old, it's only 2%. Another possibility is novelty. New experiences create richer memories, which make time feel fuller. Routine, on the other hand, tends to blur together. Then there's the peculiar nature of memory. We don't experience the present as a single instant, but as a short stretch, about 3 seconds, called the subjective present. Our brains stitch together sensory information into a flowing experience. It's not perfect. Sometimes it gets things wrong, but for the most part, it gives us the feeling of continuity, like a badly edited film that still makes sense overall. Cultural and linguistic factors influence how we think about time too. Some languages treat time as flowing left to right, others vertically. Some cultures focus more on the future, others on the past. This shapes how we plan, remember, and even how punctual we try to be. Not everyone agrees that 5 minutes late is late, especially not the person who's always 5 minutes late. Sleep and circadian rhythms are another piece of the puzzle. Our bodies keep time with internal clocks, roughly 24 hours, regulated by light and hormones like melatonin. Disrupt these cycles, and our sense of time becomes hazy. Jet lag, shift work, and insomnia all show how fragile our temporal awareness can be. The brain knows what time it thinks it is, whether or not the sun agrees. And yet, even with all these quirks, subjective time is remarkably reliable. For day-to-day survival, we may not be able to measure milliseconds by instinct, but we're quite good at knowing whether it's time to eat, sleep, or pretend to be busy. The brain's sense of time evolved to be useful, not precise, which probably explains why no one's born with a functioning sense of when to leave a party. This leads us to consider a final question. If time is this slippery, physically uncertain, biologically distorted, and culturally variable, can we ever say for sure that it's real? By now, time has taken a bit of a beating. We've seen it bend, slow, reverse in theory, and possibly not even exist at the most fundamental level. So it's fair to ask, is time real? Not just in the "my train leaves at 3 cents," but fundamentally, physically, cosmically. Does time actually exist, or is it something we've made up to cope with things changing? In one sense, time clearly does something. Clocks tick, seasons shift, humans age, less gracefully than we'd like. Physics predicts changes over time with remarkable accuracy. So whatever time is, it plays a key role in how we model and navigate the world. But whether it's a real physical dimension or just a useful bookkeeping tool is still hotly debated. Some physicists argue that time is emergent, not a basic part of reality, but something that comes from deeper processes. Sort of like how temperature isn't a single thing, but a statistical average of lots of particles moving about. In this view, time is the result of relationships between events, not a backdrop they happen against. If that sounds unsatisfying, congratulations, you're thinking like a philosopher. Other models take it further, suggesting time is entirely illusory. The block universe idea says the past, present, and future all exist equally, like a four-dimensional loaf of space-time. You only feel like you're moving through time because your brain is stuck in one slice at a time. It's not quite time as a flat circle, but it's in the same vaguely depressing ballpark. This becomes even stranger when you look at physics without time. Some versions of quantum gravity eliminate time entirely from the equations. Instead of things evolving over time, you get relationships between different states. From our perspective, this looks like change. But in the maths, nothing's actually happening. If you're wondering whether that's a satisfying answer, it really isn't. And yet, we experience time constantly. It feels real. We remember the past, anticipate the future, and grow older whether we like it or not. If time isn't real, then either our brains are very confused, or they've invented something genuinely useful. Possibly both. So, is time real? It depends what you mean by real. It's not a particle, not a force, and may not be fundamental, but it's measurable, experienced, and indispensable to how we make sense of the universe. It might not be an object, but it's definitely a structure, a framework that helps us survive and stay vaguely punctual. This leads us to a final thought. If time might be an illusion but an incredibly consistent one, what does that say about how much of reality is shaped not by what is, but by what our brains expect? If time might not be real in any deep physical sense, why do we hold on to it so tightly? The answer, unsurprisingly, is that we're not built for timelessness. Our biology, psychology, and even our grammar are structured around time. We live in it, speak through it, and think along its arrow. Without it, things get rather messy. Start with the brain. Human memory doesn't record events like a CCTV. It builds narratives, stories with a before, during, and after. That structure relies on time. Even our sense of self is tied up in it. You are who you are because you remember who you were and expect to become someone else. Remove that temporal scaffolding, and you're left with a sort of philosophical blancmange. Time also gives us a way to cope with change. Things happen. People grow up, break down, or disappear altogether. Time gives these changes a framework, a direction. It lets us grieve loss, plan for the future, and put the milk in before it expires. Without time, your entire fridge becomes an existential threat. From a practical perspective, time allows coordination. Calendars, clocks, appointments, alarms. None of it works without a shared sense of when things occur. This is civilization-level stuff. Try organizing a train network or a GCSE exam timetable without time. You'd end up with total chaos, or possibly just a very long queue at Euston. Philosophically, we also want time to be real. We want causes to lead to effects. We want actions to have consequences. And we want to believe that what we do now matters later. Strip away time, and morality becomes trickier to navigate. "Don't worry, I haven't done it yet," isn't much of a defense in court. Even in physics, the urge to keep time around persists. Quantum mechanics may work without it, and general relativity may bend it, but try building a bridge or launching a satellite without a reliable clock and see how far you get. Some theories do try to reconcile this: emergent time, thermal time, and other attempts to have their temporal cake and eat it slowly. All of this points to a rather human conclusion. Whether or not time is real, it's not going anywhere. It's embedded in our language, our science, and our everyday survival. So even if physicists eventually declare it an illusion, the rest of us will probably keep using it anyway. At least until someone comes up with a better way to schedule meetings. This leads us to consider the final question. If we can't escape time, what does it mean to live well inside it? If we can't escape time, we may as well try to live well inside it. This doesn't mean seizing the day in a dramatic flurry of skydives and scented candles. It means noticing how time shapes us, from the pace of our thoughts to the rhythms of the universe, and working with it, not against it. For a start, we might reconsider our obsession with controlling time. We chop it into hours, minutes, and seconds. We treat productivity like a moral duty, as if finishing a to-do list is some sort of spiritual achievement. But time doesn't care. It ticks on, regardless of how many unread emails you've heroically ignored. Biology offers a gentler rhythm. Circadian cycles, hormone flows, sleep phases. Our bodies already have their own clocks. The trouble is, we're often too busy overriding them with coffee, phone alarms, and late-night streaming marathons. Living inside time might mean listening to those rhythms again, even if they don't align with your favorite reality show. Culturally, we vary in how we relate to time. Some societies favor punctuality and speed. Others place more value on patience and presence. Neither is inherently better, but the modern world often rewards the fast and forgets the slow. Which is ironic, considering the slow ones are usually less stressed and have lower blood pressure. On a larger scale, we exist within geologic, evolutionary, and cosmic timelines. Your whole life, from first cry to last sigh, is a blink compared to a tree, a mountain, or a galaxy. Rather than finding that bleak, it can be grounding. If time is vast, and we are brief, maybe not every decision has to feel like a referendum on your worth. Memory and anticipation give us the illusion of control. We replay the past and rehearse the future, but all living actually happens now, where the past is done and the future hasn't shown up yet. Yes, that's a bit of a cliché, but clichés often hang around because they're annoyingly correct. So what might living well in time really look like? Noticing more, rushing less, being present without pretending it's some sort of spiritual performance, letting go of the idea that every minute must be optimized, and maybe accepting that some moments are meant to be simply endured, not improved. This leads us to one final question. If time isn't fixed, and life doesn't come with a stopwatch, then what, if anything, truly gives time its meaning? Time, by itself, is just a measure of change. One thing happens, then another. A planet spins. A tree drops its leaves. A sandwich goes stale. None of this means anything until someone pays attention. Meaning isn't built into time. It's something we bring to it. The ticking is neutral, the living is not. Humans are meaning makers. We notice beginnings and endings. We celebrate anniversaries, mark birthdays, and mourn losses on specific dates. We assign significance to dates on calendars, even though the universe doesn't. The 31st of December means nothing to a black hole. But to us, it's a reason to wear glitter and reflect on how many gym memberships we didn't use. Meaning also comes from memory. Our past isn't just a record of events, it's a story we tell ourselves about who we are. But memory is selective. It distorts, edits, forgets. Even so, we stitch these fragments into a timeline that feels coherent, even if it isn't always accurate. It's the narrative that matters more than the precision. Then there's anticipation, planning, hoping, dreading. These give the future emotional weight. A job interview, a wedding, or a hospital result all feel like they exist before they happen. In truth, they don't exist at all yet, but we react to them anyway. So even imagined time can shape what we do in the present. Shared experiences also create meaning. A group of people going through something together, whether it's a football match, a funeral, or just surviving a really long meeting, creates collective time. That's why some moments seem to stretch out, while others flash by. Time isn't just what the clock says, it's what it feels like. Curiously, the most meaningful moments often happen when we forget about time completely. A deep conversation, a walk in the woods, a good book, these don't feel like ticking seconds. They feel timeless, which is ironic considering the rest of our lives are spent trying to manage time with calendars and alarms. And yet, time still ends. For people, for species, for stars, maybe even for the universe itself. That looming ending makes the middle feel significant. Meaning, then, might be the brief light cast between two darknesses. The bit where things are happening, however temporarily. Not exactly cheerful, but rather motivating. In a better get on with it sort of way. This leads us, finally, to the quiet truth at the heart of all this. Time doesn't come with meaning included, but life does. And while the physics of time might be uncertain, what we choose to do with it isn't. For all our effort to measure, manage, and find meaning in time, there's a rather awkward possibility lingering in theoretical physics. Time, as we know it, might not be real. Not real in the same sense as gravity, mass, or the haunting memory of your teenage haircut. Just a useful way of organizing change, not a fundamental feature of the universe. Let's start with general relativity. In Einstein's model, time is tied to space. It's not some independent background ticking along, it's a dimension, like up or sideways. The presence of mass warps both space and time. That's why clocks run more slowly near a massive object. But if time can speed up or slow down depending on where you are, how real is it really? Now jump to quantum mechanics. Here, things get even less cooperative. The equations that describe quantum systems don't need time, they just describe how systems relate to each other. Time only pops out when we observe changes, like a particle moving, or a cat being alive, or not. And yet, the underlying maths doesn't demand a flowing timeline. Some physicists, like Carlo Rovelli, have argued that time is not fundamental, it's emergent. In other words, time might arise from deeper, timeless laws when you zoom out far enough. A bit like how temperature doesn't exist at the scale of individual molecules, but becomes meaningful when you look at a crowd of them rushing about. This leads to a strange possibility. The flow of time, the sense that there's a now, a past, and a future, might be a feature of how our brains experience the world, not how the universe fundamentally works. Evolutionarily speaking, being able to remember what just happened and guess what might come next is very useful. Doesn't mean it's the ultimate truth. There's even an approach in physics called timeless quantum gravity. In this model, the universe is described without time at all, just a series of relationships between things. Events don't happen in order, they just are. No before, no after. No Tuesdays. No weekends. Of course, not everyone agrees. Time could still be fundamental, just misunderstood. Or it might work differently depending on the scale you're observing. But what's clear is that time is far less solid than it seems. It bends, warps, vanishes in black holes, and might not even be real at the deepest level of reality. Which brings us to the final question. If time might not exist, and yet we clearly live inside something we call now, then, what exactly is now? We live inside a moment we call now. It feels obvious, this instant, this breath, this sentence, but the more closely we examine it, the less clear it becomes. What exactly is now? Is it a real feature of the universe? Or just something our brains make up to stop us panicking? Physics, famously, doesn't care much for now. Einstein showed that different observers can disagree on whether two events happen at the same time. What's now for you might already be then for someone moving quickly in another direction. Not ideal for train timetables or birthday parties, come to think of it. From the point of view of space-time, all moments, past, present, and future, exist equally. This idea, called the block universe, suggests that time doesn't really flow. The universe is like a four-dimensional loaf of bread. Your birth is in one slice, your retirement in another, but they're all baked into the loaf at once, depressing or reassuring, depending on how your week's gone. So, why does now feel so special? Neuroscience gives one possible answer. Our brains process the world with a slight delay, roughly half a second. To avoid confusion, they stitch together sensory input into what feels like a unified moment. It's a bit like watching a live broadcast on TV. It feels immediate, but there's always a small lag. That stitched together feeling gives us a sense of continuity, a flow from one moment to the next. But the sensation of now might not be a window onto reality. It might be a trick of biology. A useful one, to be fair. Living in a permanent state of before or after wouldn't be great for crossing roads. Interestingly, some theories suggest that consciousness itself might create the illusion of now. We don't observe a flowing time, we experience being in time. Our thoughts line up like pearls on a string, but the string might be optional. The pearls may exist independently, and we're just very attached to storytelling. If now is just an illusion, that doesn't make it meaningless. Most of life happens in now. Love, pain, laughter, burnt toast, it all unfolds here. Even if now isn't objectively real, it's subjectively essential, which, in the grand scheme of things, might be just as important. This leads us to one final, awkward question. If time might not flow, if now might not be real, and if the universe doesn't particularly care, then what, exactly, are we supposed to do with the time we think we have? By now, we've picked apart time from almost every angle. Physical, philosophical, even biological. We've questioned whether it flows, whether it exists, and whether now is anything more than a mental placeholder. So, what are we meant to do with this strange, possibly fictional thing we call time? Well, even if time isn't real in some ultimate physical sense, it's undeniably useful. Whether or not the universe cares about Tuesdays, your dentist definitely does. Our lives are structured by time. Waking, working, aging, and eventually. Well, not. Time gives shape to what would otherwise be a continuous blur of experience. There's also the simple fact that we feel time passing. That sense of movement, from past to future, is deeply woven into our psychology. It lets us learn, plan, regret, and hope. It gives us a story to live inside. And for better or worse, we humans are particularly fond of stories. Of course, once you realize that time might not be fundamental, you could fall into a bit of a philosophical hole. Does any of it matter then? If the future already exists, can I just stay in bed and let fate do its thing? Well, yes. But your mattress isn't going to pay the rent, is it? Instead, perhaps there's value in treating time less like a cosmic command and more like a creative constraint. A limited canvas. You don't need time to have meaning in order to make meaning within it. That might sound a bit like a motivational poster, but at least it doesn't feature a cat hanging from a branch. Physics doesn't tell us how to live. It just tells us what we're living inside. Time, whether real or imagined, is the backdrop to every choice we make. And until someone invents a working time machine or remembers where they parked it, this is the only timeline we've got. So what should we do with time? Maybe the best answer is also the simplest. Use it. Even if it's an illusion, it's a shared illusion. It's how we relate to each other, how we make plans, how we measure change. It's what gives us the concept of before dinner and after dessert. And, arguably, that's civilization. Which brings us, naturally, to one final possibility. If time might not exist, and now might be a fabrication, then is it still possible to travel through it? The idea of traveling through time has been a favorite of science fiction for over a century. From Victorian gentlemen in brass machines to teenagers in sports cars, we've imagined all sorts of ways to skip forwards or backwards through history. But strip away the plot devices and pithy catchphrases, and the real question is, could it actually work? Surprisingly, physics doesn't rule out time travel entirely. In fact, it quietly allows it, under some rather inconvenient circumstances. Special relativity already lets us move into the future. The faster you go, the slower time passes for you. Travel at near light speed, and you could return to Earth having aged minutes, while everyone else has aged decades. Though you might find your favorite cafe has been replaced by a laser hairdressing emporium. Traveling into the past, however, is a trickier business. General relativity, which describes how gravity bends space-time, does allow for hypothetical structures called closed time-like curves, essentially loops in time. In theory, you could enter one end and pop out earlier than you went in, which sounds handy for fixing mistakes, although it's probably a bit late for my haircut in year 9. One proposal involves something called a wormhole, essentially a shortcut through space-time, connecting two distant points. If one end of a wormhole were accelerated to near light speed and brought back, relativity suggests it could become offset in time relative to the other. Step through one mouth, and you might emerge in the past. All very elegant, provided you've got access to negative energy and a casual disregard for paradoxes. Ah, yes. Paradoxes. The universe isn't too keen on them. The classic is the grandfather paradox. Go back in time, accidentally erase your grandfather, and whoops, you were never born to do it in the first place. These contradictions suggest that either time travel to the past is impossible, or the universe has a very strange way of protecting its timeline. Perhaps by branching into alternate histories, quantum mechanics might provide a loophole. Some interpretations suggest that all possible outcomes of a quantum event actually happen in different parallel worlds. So if you did go back and make a catastrophic change, it wouldn't affect your own timeline. You'd simply create a new one, where trousers are never invented and everything smells faintly of cinnamon. Of course, this is all highly speculative. There's no experimental evidence for wormholes, time loops, or parallel timelines. Most physicists treat time travel to the past as extremely unlikely, if not outright impossible. Still, it hasn't been proven impossible, which is probably why so many researchers still get questions about it at parties. This leads us to a more subtle possibility. What if time travel doesn't mean physically stepping into a machine, but changing how we perceive or influence time itself? If physical time travel seems a bit far-fetched, what with the need for wormholes, negative energy, and possibly a degree in quantum plumbing? Perhaps there's another way, a quieter, more personal kind of time travel. Not through space, but through memory, attention, and imagination. Humans are, as far as we know, the only species capable of mentally projecting themselves into different points in time. It's called mental time travel, and it's something you probably did before breakfast, remembering yesterday, worrying about tomorrow, and wondering where your socks keep disappearing to. This ability is deeply tied to memory. Our brains don't just store information like a filing cabinet, they reconstruct experiences when we recall them. It's an act of imagination, not a replay. That's why memories can shift over time, and why you're convinced your childhood dog was twice the size it actually was. Interestingly, this feature isn't just useful for remembering. It's critical for planning. The same brain systems we use to reflect on the past are also used to imagine the future. Without memory, you can't build expectations, prepare for outcomes, or even make a to-do list that isn't just eat biscuit, repeat. Our sense of time's passage is also weirdly malleable. When you're bored, time drags. When you're stressed, it flies. And when you're watching a progress bar that says 1 minute remaining, time collapses entirely, and you question the nature of reality itself. It's not just perception, it's attention. The more information your brain processes, the longer that stretch of time feels. Some experiments have shown that meditation, focused breathing, or even altered states of consciousness can shift how we experience time. This isn't mysticism, it's neurology. Our internal clocks, governed by brain chemistry and body rhythms, can stretch or compress time depending on what we're doing, how alert we are, and what we expect. And then there's nostalgia, that particular form of backward mental travel. It's not just sentimentality, it can actually serve a purpose. Revisiting the past, emotionally or cognitively, helps reinforce identity and connection. Even if the 90s weren't as good as you remember, they still serve as a mental anchor in a world that increasingly feels like it's buffering. Psychological time travel reminds us that we're not stuck in the present. Our minds are constantly darting backwards and forwards, weaving a timeline from fragments. It's not always accurate, and it's certainly not tidy, but it's one of the things that makes us human. This leads us to one final curiosity. If we're so good at mentally escaping the present, what actually is the present? And can it be pinned down at all? We often talk about living in the moment, but what exactly is a moment? When we say now, are we referring to a measurable point in time, a fleeting instant, or just the vague feeling that things are currently happening? Like a Wi-Fi signal, now feels strong until you try to pin it down. In physics, there's no special place for the present. Einstein's theory of relativity tells us that what's now for you might not be now for someone else, especially if they're moving very fast or in a different gravitational field. Time isn't universal. It's local, shaped by where you are and how you're moving, which makes planning surprise parties quite complicated on a spaceship. This idea is known as the relativity of simultaneity. It means two events that seem to happen at the same time in one frame of reference might not be simultaneous in another. So, whilst your toaster pops at exactly 7:01 a.m. on Earth, someone flying past at near light speed might disagree. Not because they hate breakfast, just because their clocks are different. From a physics perspective, time is treated as just another dimension, like space. There's no cosmic spotlight sweeping across the universe to illuminate now. All points in time, past, present, and future, are equally real. This view is called the block universe. It's not terribly intuitive, but then again, neither is explaining why teenagers need 14 alarms to wake up. Neuroscience adds another wrinkle. Our brains aren't instantaneous. They take time to process information. The image you see, the sound you hear, even the thought you have about it, all take a few hundred milliseconds to come together. So your conscious now is really a best guess. A neatly stitched together package of slightly outdated data. This also explains why you can see lightning before you hear thunder, and yet still feel like they're part of the same event. Your brain delays processing just long enough to line things up. It's not cheating, just efficient buffering. Like a live stream that's 1 second behind, but still convincing. Even more curiously, different senses operate on slightly different timelines. Touch, sight, and hearing all travel through different channels at different speeds, but your brain edits them into a single, unified experience. It's quite a juggling act. If your brain were a film editor, it would win an award for continuity, assuming the ceremony started on time, which of course it wouldn't. So, is now real? Physically speaking, not especially. It doesn't exist as a unique part of the universe. But psychologically, it's essential. Our sense of the present gives us a platform for action, reflection, and probably regret about eating that third biscuit. Without now, there'd be no sense of being at all. This leads us to one final mystery. If time isn't fixed, and now isn't absolute, what exactly is flowing? If time doesn't have a universal now, and the past, present, and future are equally real in the block universe model, then why does it feel like time is moving? Why does it seem to flow from earlier to later, dragging everything, including us, along with it? You'd be forgiven for thinking the universe has somewhere to be. In physics, there's no fundamental reason for time to flow. The equations that describe the laws of nature, whether it's Newton's, Einstein's, or quantum mechanics, are reversible. They don't prefer one direction over the other. If you filmed most physical processes and played them backwards, the maths wouldn't care. Your coffee unmixing its milk, however, would probably make you suspicious. So where does this sense of direction, this so-called arrow of time, actually come from? The most accepted explanation involves entropy. That's a measure of disorder. According to the second law of thermodynamics, entropy tends to increase over time. Things go from tidy to messy, not the other way round. Basically, the universe is slowly falling apart in a very orderly fashion. This gives us a kind of directionality. We remember the past because it was lower in entropy. We anticipate the future because it'll be higher. Ice melts, but puddles don't spontaneously freeze into elegant cubes. Not because it's impossible, but because it's wildly improbable. Nature tends to prefer the mess. Interestingly, entropy also links to memory. We form memories in one direction of time, never backwards. That's not just a psychological quirk, but a reflection of thermodynamic change in our brains. You never remember tomorrow, no matter how much you revise, which, for most students, is a convenient excuse. Some physicists argue that the flow of time is entirely emergent. It arises from statistical patterns, not from deep laws. In this view, time doesn't truly pass. We just happen to live in a region of the universe where entropy started low and keeps rising, giving the illusion of progression. A bit like pretending a treadmill is going somewhere just because your legs are moving. Others propose that time's flow might be tied to quantum mechanics and how probabilities collapse into definite outcomes when we observe them. But even that doesn't produce a universal direction. It just adds another layer of uncertainty, which, let's be honest, physics is already quite good at. So no, time might not actually flow at all. What we perceive as movement through time could just be the way our brains interpret a growing pile of events in an increasingly disordered cosmos. We're not traveling through time. We're accumulating entropy in quite a stylish way. This leads us to one final question. If the flow of time is an illusion, could it ever stop altogether? If time doesn't really flow, then could it, at some point, come to a full stop? Not just feel slower or seem to drag, like double maths on a Monday, but actually cease entirely. It's a strange idea, and one that requires us to examine what we really mean by time stopping. In day-to-day life, time stopping would probably mean all motion freezing, no clocks ticking, no atoms jiggling, no thoughts forming. But from a physics perspective, time is simply a dimension. Like space, it's part of the structure in which things happen. For time to stop, the universe would need to reach a state where change is no longer possible. The most well-known version of this is heat death. That's the hypothetical final state of the universe. Cold, dark, and utterly boring. No usable energy. No stars shining. Just particles floating about in maximum entropy. Everything would have reached equilibrium, meaning nothing more interesting can happen. Essentially, it's the cosmic equivalent of the Wi-Fi being down forever. In such a state, time would still technically exist, but it would lose its usefulness. With no events occurring, no clocks ticking, and no observers around, it becomes difficult to distinguish one moment from the next. The universe would still be aging, but with all the excitement of a waiting room with no magazines. There are other, more dramatic ways time could end. One is inside a black hole, where according to general relativity, time behaves very oddly. From the outside, it looks like time slows down near the event horizon. But for someone falling in not recommended, it continues as normal, until it doesn't. At the singularity itself, the math stops working entirely. So does physics, so does your body, unfortunately. Another possible fate is the Big Crunch. the reverse of the Big Bang, where the universe collapses back in on itself. In this model, time might reverse, compress, or again, lose all meaning as the very fabric of space-time folds up. It's not clear whether anything would be around to notice. Hopefully not, really. And then there's the more speculative idea. What if time is quantized, made of tiny, indivisible chunks? If so, then the smallest possible unit of time is the Planck time, around 10,043 seconds. If we ever reached a state where not even one tick of that clock could occur, well, time would effectively be frozen, like a paused film, but with no option to press play again. So, could time ever truly stop? Possibly, but not in the way it feels when someone says, "We need to talk." In reality, it would require the universe to become so still, so uniform, that nothing can change at all. No clocks, no causes, no effects, just quiet. This leads us to consider one last question. If time has a beginning and an end, where exactly are we in all of it? Having explored beginnings, endings, and the unnerving possibility of time grinding to a halt, it's worth asking, where do we find ourselves right now in the grand timeline of the universe? Are we early, late, or halfway through some 100-billion-year existential PowerPoint? Let's start with the basics. The universe is about 13.8 billion years old. Earth is just over 4.5 billion. Humans, at least in our modern form, have been around for a mere 300,000 years. So on the full cosmic scale, we've appeared very recently. If the universe were a calendar year, we'd have shown up on 31st of December at about 11:59 p.m. clearly, not early birds. What about the universe itself? How far along is it? That depends on what you believe will happen in the long run. If we're headed toward heat death, where everything slowly fades into cold stillness, then we're still in the early part of the story. Stars are still forming, galaxies still collide. The lights are very much on, but it's also true that star formation peaked around 10 billion years ago. The universe is now more passive than productive. Galaxies aren't churning out stars as they once did. So in that sense, we might already be in a bit of a cosmic middle age. The universe isn't dying just yet, but it has stopped throwing wild parties. Zooming in, the Sun is about halfway through its life cycle. It's got another 5 billion years or so before it swells into a red giant, likely consuming the Earth in the process. Bit of a harsh retirement plan. So, for life on Earth, we're comfortably midstream, though it probably wouldn't hurt to look into a few escape plans. On the human scale, we're even trickier to place. Civilization. Cities, writing, grumbling about traffic, has only existed for around 6,000 years. That's not even 0.1% of human history. Whether we're in our infancy or approaching the end of our run depends entirely on whether we get our act together or don't. It's possible we're at a tipping point. Climate change, AI, space travel. These could mark a shift to something entirely new, or they could be our final flourish before fading out. It's a bit like being at the cinema and realizing you've no idea how long the film is, or whether the snacks will last. So, where are we in time? In one sense, right in the middle of everything that matters to us. In the wider cosmic timeline, though, we've only just arrived. The curtain has been up for quite a while, and the closing act, if there is one, won't happen for billions of years. This leads us to consider something more immediate, how time feels, here, now, for us. We live in time. We measure it, follow it, worry about it, and occasionally waste vast amounts of it scrolling through things we don't even like. But despite its steady beat, time doesn't feel steady. Sometimes it crawls. Sometimes it vanishes. And strangely enough, it's rarely honest about how much of it has just passed. Psychologically, our sense of time is more impressionistic than precise. For example, time seems to move faster as we age. This isn't just nostalgia or something you notice when you start saying things like, "Wasn't it just Christmas?" It's down to proportion. A year to a 5-year-old is 20% of their life. To a 50-year-old, it's just 2%. It's not time speeding up, it's our perspective shrinking. Then there's the influence of emotion. Moments filled with anxiety, boredom, or discomfort feel longer. Meanwhile, joyful or immersive experiences seem to end far too quickly. Waiting for a kettle to boil when you're already late feels like a century. Watching something you enjoy, strangely, doesn't last long enough to even finish your tea. Attention plays a key role too. When we're highly focused, especially in novel situations, we process more details. That gives us the sense that time is stretching. It's one reason why new experiences, first days at school, unfamiliar cities, feel richer in memory. Whereas routine flattens time. If every Tuesday looks the same, you won't remember much of any of them. There's also a peculiar trick in memory. Our brains tend to store the most intense moments and the final moments of any experience. Known as the peak-end rule, it explains why holidays with one spectacular sunset and a decent flight home feel great overall, even if most of it involved arguing about directions. Oddly enough, we're better at remembering events than how long they lasted. Ask someone to describe a childhood summer, and they might recall bike rides or the smell of cut grass. Ask how many days that summer lasted, and they'll struggle. Time doesn't store itself in our memory. Experiences do. And of course, technology has meddled with our sense of time too. The pace of digital life encourages immediacy, but it also fragments attention. You can spend an hour watching short videos, and at the end of it, feel like none of it actually happened. A sort of time coma. 1 minute you're checking the time, the next it's Thursday. So, our experience of time is hardly objective. It's colored by emotion, shaped by memory, distorted by routine, and hijacked by modern distractions. Yet, we treat time as if it's this fixed, reliable thing, ticking along evenly like a metronome. This leads us to consider one final idea. If time feels different depending on who and where you are, is time ever truly shared? And that brings our journey to a gentle close. If you're still with us, you're welcome to drift off with another of our sleepy deep dives. Until then, rest well and good night.